The tyrannosaurs were around from the mid-Jurassic to the very end of the reign of the dinosaurs. The secret to their success, which would have been a much meatier endeavor had that pesky rock not hit so close to home, is multi-directional. One of the many of their secrets lied in their feet, and a new research paper cut them open to prove it. During the late Cretaceous, tyrannosaurids were large, ecologically important predators that lived in both North America and Asia. Adults of later tyrannosaurids were 2 orders of magnitude bigger than the next largest adult terrestrial carnivore. This is rare among terrestrial carnivores. The success of tyrannosaurids and their relatives among the larger tyrannosauroids has been linked to their unique feeding adaptations, such as fused vaulted nasal bones, a broad, twisting and bending resistant skull, an expanded secondary palate, high bite and neck muscle forces, and strong, bone-pulverizing teeth. These adaptations came about in piecemeal as adults got bigger, and Tyrannosaurus rex, Tarbosaurus bataar, and Zhushangtyrannus magnus, the last and largest tyrannosaurids, had the most of these adaptations. In addition to features that helped them eat, postcranial or bodily changes that happened before tyrannosaurids diversified when tyrannosauroids were still small may have helped the group become the only large predators in the environment. Derived tyrannosauroids, like tyrannosaurids, had body parts that might have made them more agile than other theropods. For example, they had large leg muscles to help them turn their bodies, and their bodies were more compact from nose to tail, which made quick turns easier. At the same time as other Cretaceous theropods, such as ornithomimids, alvarezsaurids, troodontids, and some sainognathed oviraptorosaurs, tyrannosaurs developed the arctometatarsalia metatarsus, an elongated and relatively narrow, antero-posteriorly strong metapodium with a proximal splint and distal expansion of the third metatarsal. Those were a lot of anatomical vocab words to throw at you, but let's take a look at this bone so we can get a better idea of what those words mean. Right, okay, so here we go. So the near end of the middle metatarsal is squeezed between the metatarsals around it. It creates this sort of fused, triangular, pinched mash of bone. Whether tyrannosaurs were mostly hunters or mostly scavengers, being able to move faster and cover more ground would have been, a little bit helpful. But the most unusual parts of the arctometatarsus show that tyrannosaurs could move extra quickly. A wedge and buttress constriction of the central third metatarsal bone between the outer bones and discrete areas of roughness on the surfaces where the metatarsals connect to each other at the end. If these rough surfaces were connected to ligaments, they would have made the foot stronger and when moving in different directions. In their 2003 paper, paleontologist Eric Snively and Anthony Russell found that the kinematics of the arctometatarsalia foot would prevent splaying at high footfall energies because the central metatarsal bone is moved forward and the outer metatarsals are pulled in toward the flat midline of the foot. Other vertebrates put more weight on their individual, spread out outer metatarsals, like what happens to our first toe when we quickly speed up or slow down. Intermetatarsal kinematics in tyrannosaurids, on the other hand, would spread the load and forces more evenly across the metatarsals. This would let them move with more force while keeping the stresses, force over area, and tissue safety factors the same. Then, in 2002, Snively and Russell found that the ligaments in this foot structure are most likely needed to keep the proximal splint of the central metatarsal from breaking. These kinematic and structural mechanical hypotheses need to be tested more thoroughly. If the hypotheses are true, these ligaments would make sense for Tyrannosaurs' ability to catch prey, just like adaptations that make predatory animals more agile in similar ways. Going back to their 2003 work, Snively and Russell also inferred that Tyrannosaurs had intermetatarsal ligaments based on large-scale osteological correlates. This was only an inference rather than full-on tests. Osteological correlates, or textures and shapes of bone that often correlate to certain soft tissue structures, muscles, and ligaments, have been looked at more and more in recent decades. You may have heard of them in discussions on reconstructing soft tissues on dinosaurs, but they can also help understand other squishy stuff. They have also come under fire by some researchers, and for good reasons, but we are not here for those reasons right now. This anatomical inference can be tested by other lines of evidence and used as a foundation for functional interpretations. This brings us squarely into the realm of research recently published by a team that includes Laura Suring, Michael Burns, Eric Snively, Daniel Barta, Thomas Holtz, Anthony Russell, Lawrence Whitmer, and Philip Curry in the Journal of Vertebrate Anatomy, Morphology, Paleontology. This team used scanning electron microscopy and histology to 1. Look for smaller scale correlates of ligament attachment, which could disprove the idea that there were ligaments, and 2. See if the direction of ligament insertion is consistent with the idea of splay negating kinematics, proposed by Snively and Russell all the way back in 2003. A fibroblast is a type of cell that makes extracellular matrix and collagen, makes the framework for animal tissues, and is important in the healing of wounds. They are the most common type of cell in an animal's connective tissue. Under tension, fibroblasts in the periosteum, which is a membrane that covers the outside of all bones except for the parts of long bones that are in the joint space, lengthen, and parallel osteons form deep to the attachment surface. The osteon is the basic functional unit of most compact bone, found in a lot of bones of mammals, birds, reptiles, and amphibians. Ligaments and tendons leave microscopic traces of their attachment to these bones, and these traces can be found on the surface of attachments that are put under a lot of stress. There are also ligament entheses, or the tendon-to-bone attachment site, in transitional fibrocartilage, which makes the bone surface rough. Fibrocartilage is a thick white tissue that has a very fibrous feel. It makes the intervertebral discs in the spine and the menisci in the knee, as well as smaller structures like the glenoid and acetabular labra and the lining of bone grooves where tendons go. This all falls under the study of histology, which is the study of microscopic tissue structures. These histological marks can be used to test hypotheses about the presence of ligaments by distinguishing ligament and tendon entheses of attachment from other rough bone surfaces, such as vascularity striated textures that appear during archosaur growth. With the help of scanning electron microscopy and histological preparations of an adult tyrannosaur metatarsal bone, the research team were able to see if the intermetatarsal ligaments would have helped the tyrannosaur move faster. As a possible control for tyrannosaur ligament inferences, the researchers looked at a metatarsal thin section from the early theropod Coelophysis borii that was taken from a spot with no large entheses. The Coelophysis histology tests the idea that tyrannosaurs had a lot of ligaments, and it could show that this idea is wrong. If the evidence is falsified, the Coelophysis and tyrannosaur specimens would have similar correlates. Neither would have microscopic correlates, and the Coelophysis metatarsal would have fine-scaled correlates that aren't present in the tyrannosaur metatarsal. Also, Sharpie's fibers were found in the second metatarsal of an alvarezsaur, so the researchers looked for them in other coelurosaurs with arctometatarsalien or subarctometatarsalien feet to see if they were present in tyrannosaurids. Methods. The team looked at the macroscopic correlations for ligamentous attachments in the fossils that Snively and colleagues looked at in 2004. plus a lot of new tyrannosaurid metatarsals that were just found at the University of Alberta Laboratory for Vertebrate Paleontology and the Royal Tyrrell Museum of Paleontology. The team also looked through the scientific literature for descriptions of histological correlates in the metatarsals of other coelurosaurs. Paleohistological analysis was done on specimen UALVP 49310, a tyrannosaurid bone. This is a piece of Gorgosaurus libratus, third metatarsal from the Upper Campanian or Upper Cretaceous of the Dinosaur Park Formation in Alberta, Canada's Dinosaur Provincial Park. Arctometatarsal third metatarsals have a posterior constriction that forms a ridge and are shaped like a triangle at the end, which is also called a plantar constriction. UALVP 49310 is a Gorgosaurus third metatarsal because it has a curving, distally extended posterior constriction. This is different from Daspletosaurus, which has a straighter, wider, oblong, and less wedge-like distal constriction. Paleohistological analysis was done by cutting thin sections all the way through the metatarsal diaphysis. The cut started at the part of the central roughness on the side with the most protrusions. Also, 1 centimeter diameter cores were cut out of the bones and split down the middle so they could be put on slides. Before cutting the samples into pieces, they were stabilized with Buehler Epothin, low viscosity resin, and hardener. Standard petrographic procedures were used for cutting and grinding. Interference colors were used to measure the thickness of the sections, which were ground to between 60 and 80 micrometers, depending on how well the interesting internal structures could be seen. With a Nikon Eclipse E400 polarizing microscope, the sections were looked at in both plane polarized and cross-polarized light. Scanning electron microscopy was used to take pictures of the surface texture of the 4 cores that were used for histologic analysis. The cores were covered with about 100 angstroms of gold, and a JL 6301 FE scanning electron microscope was used to look at them. The accelerating voltage was 5 kV, and the working distance was 15 millimeters. A Coelophysis metatarsal had already been cut and sectioned for the 2016 to 2017 American Museum of Natural History Dinosaurs Among Us special exhibition, which helped compare fossils in this study. The specimen was cut in half across its whole diaphysis near the end closest to the body. The sampled piece was set in epoxy cut with Buehler Isomet 1180 low-speed saw, ground until it was clear, and viewed with a Nikon OptiPhot 2 petrographic microscope in both plane polarized and cross-polarized light. Results. There are large ligament scars on the Tyrannosaur third metatarsal that are similar to those found in other theropods. Snively and Russell say that, unlike other large theropods, Tyrannosaur third metatarsals have huge, rough, ovoid facets at the end of the articulating surfaces of the second through fourth metatarsal. Other features are far away from this scar or add to its shape. The primary tuberosity is an oblong, tuberous ridge that runs along the front edge of the large distal scar in all tyrannosaurids, no matter how old they are or what kind they are. For those curious, a tuberosity is a rounded protuberance at the end of a bone to which a muscle or tendon is attached. The size of the rough surface texture on the primary tuberosity seems to depend on age. In smaller Tyrannosaur third metatarsals, which are thought to be juveniles, this texture is less developed and covers less surface area. A smooth, scalloped area can be seen distal to the primary tuberosity and dorsal to the posterior collateral ligament pit. However, Tyrannosaurus rex's scalloped surface is smaller and less deep than those of other tyrannosaurids. Albertosaurian tyrannosaurids, like Gorgosaurus libratus and Albertosaurus sarcophagus, have a secondary tuberosity along the posterior edge of the scallop, and all juvenile tyrannosaurids have scalloping that is deeper and has clearly defined edges. Tyrannosaurus rex fossils have a bigger version of a smaller, circular accessory tuberosity that is often found near the base of the main tuberosity on the back. 3 of the 4 core samples have periosteal bone in the outermost part of the cortex. Periosteal bone, or the periosteum, is the sheath outside your bones that supplies them with blood, nerves, and the cells that help them grow and heal. Sharpie's fibers, which connect the periosteum to the bone and are a matrix of connective tissue made up of bundles of strong, mostly type 1 collagen fibers, show that ligaments went into the periosteal surface at angles of 20 to 50 degrees, but their direction relative to the periosteal surface is the same in each core. Sharpie's fibers are angled in more than one direction relative to the bone surface where the surface is roughest. This is typical of strong entheses. Sharpie's fibers grow in the same direction on the outside and deep to lines of stopped growth when lines of arrested growth are visible in a thin section, as they are in alligators that are still alive. The scanning electron microscopy showed that the rough bone surface had pits, which is similar to how tight ligaments connect to bones in modern animals. The Tyrannosaur's bones were made up of mineralized ligaments that held the muscles in place inside the bone. Coelophysis didn't have such strong ties. As in living vertebrates, it is thought that Gorgosaurus metatarsal surface pitting and Sharpie's fibers were caused by a mechanobiological process directly related to stress transfer at the point where the ligament meets the bone. Why are these entheses on the arctometatarsus of tyrannosaurs so long and strong, and how did natural selection shape their likely adaptive roles? As said in the beginning, it is thought that the confined ligaments had a direct effect on how fast long-footed tyrannosaurs could move. The ends of the limbs of large living vertebrates often have to deal with complex loads and can break when overloaded, like when horses move quickly and nimbly. When a bigger body tries to move, it puts more stress on certain parts of the skeleton because it has to deal with more twisting forces. These changes in size, shape, material properties, and/or function are called adaptive allometries, and they become more noticeable when the body weight goes over 300 kilograms. The arctometatarsus shows changes in architecture and ligaments that are consistent with the tyrannosaur's small body size and large leg muscles, which suggest that they were more agile. These changes can be seen in the macro and micro trace fossils of soft tissue. The research team found that the connection between the ligament and the bone is related to the ability to move quickly. Areas of calcified ligamentous attachments are able to handle higher stresses at the ligament-to-bone interface. With a tensegrity-style mechanism, comprehensive forces from the foot could have been turned into tension by parallel groups of microscopic entheses. Together, these large ligament connections would have spread out local tensile stresses to make the tyrannosaur foot stronger. The fact that the distal scar got close to the pits of the collateral ligaments shows that the tyrannosaur leg were strengthened more than other theropod legs were by their ligaments. This is especially true for adult Tyrannosaurus rex, whose scars got bigger near the body so they could cover a bigger area. The three tuberosities face in different directions, giving the ligaments more surface area to hold onto. This makes the ligaments work better by transferring regional torsional stresses to reduce intermetatarsal splay, or lateral spreading of the bones from each other. Allosaurids, about the same size as an adult Tyrannosaurus, don't have these distal attachments. This includes Mapusaurs, Acrocanthosaurs, and a large Carcharodontosaurid included in this study. So the adult T-Rex's relatively large ligaments aren't just there to support its weight. Like its smaller relatives, they probably helped it move around well for its size. Large foot ligaments and dynamic calculations suggest that tyrannosaurids were agile, which is in line with the traits of their nerves and senses. Compared to other large theropods like Allosaurus and Ceratosaurus, the semicircular canals of tyrannosaurids, especially the lateral canal, are larger. This suggests that the animal would have had rather good gaze and head stabilization reflexes, which, kind of important for finding and catching prey. Based on the shapes and sizes of the semicircular canals and their neural connections with the visual system to stabilize their gaze, the structure of the inner ear of mammals, birds, and large dinosaurs has been linked to their ability to move quickly. Even though there haven't been any quantitative studies of dinosaurs like those done on mammals, the fact that the canals of agile mammals like cheetahs, bats, and primates, and birds are long is a good sign that tyrannosaurs could move quickly as well. As with other small Coelurosaurian dinosaurs, juvenile tyrannosaurs would benefit more from synapomorphically large canals for full-body maneuvers than adult tyrannosaurids, who are slower to react and turn. Once in range, adults could use their vestibular reflexes to move their heads and necks quickly and with control. In the latest Cretaceous terrestrial communities of Asia and North America, tyrannosaurs were the only large carnivorous dinosaurs. However, in earlier dinosaur-dominated ecosystems, different theropod clades, like ceratosaurs, megalosauroids, allosaurids, and various coelurosaur groups, usually had representatives in different adult size classes. The Tyrannosauroidea, the more inclusive clade of which the giant Tyrannosauridae are the last, largest, and most derived, lived from the Middle Jurassic onward. At the moment, there isn't enough direct evidence to say whether the change from ecosystems with many large theropod families to ones dominated by tyrannosaurids was caused by competition or by decline and taking advantage of new opportunities. No matter what happened, the changes to the arctometatarsus that made the animals more agile first appeared in animals with smaller bodies and became useful even in animals with the biggest bodies. The unique arctometatarsus of the Tyrannosaurid would have made it easier for the tyrant dinosaurs to catch prey. With external and internal microscopy showing its faded soft tissues, a Tyrannosaur's small step becomes a small step toward understanding a vivid past, said Dr. Eric Snively. The details of Tyrannosaur feet not only answer a question that has been around for a long time, but they also have implications for human health. People are the best long-distance walkers and runners of any animal today, but injuries to ligaments and tendons are common and make up about 30 to 50% of all sports injuries. Tendons and ligaments can get pulled if you work out too much. Knowing how these structures attach to bones, even in animals that are no longer alive, like dinosaurs, can help humans avoid these kinds of injuries. We hope that figuring out how tyrannosaurs change their skeletons to stay functional at the limits of animal size will help us figure out how to fix and improve human skeletons after they are hurt or get old, Dr. Laura Suring said. This research is another step toward that goal. For more interesting stories about nature, the history of life, or what goes bump in the night, subscribe, hit the bell icon for updates, like this video, and drop a comment in the comment section below. Thanks for watching. Special thanks to my elephant tier patrons: Arda Bear, Biotiverse, Christoph Hubinger, Dinosaur, Isaiah Garza, PA Brew News, Ray, Rudy Redgrave, Smiling Walrus. And another thanks to my Tyrannosaurus tier patrons: Iberospinus, Iron Bladesman, Swaffles is Weird, Teeny Dragator, The Dogman,